All right, section 17.1, 17.2, electrochemistry, electrochemical cell, standard reduction potentials. For the worksheet, do number 1A and B. If you want to do C, you can. It's a little bit longer bonus, and I'll eventually talk about that. You need to know how to do that. It could pop up, but just again, it's more like the extra high level 4 or 5 AP score question. Not too bad, just a little bit more involved. Then after you do those, so just say you do 1A and B, that's two cell calculations. Then look at the questions at the end, 3, 4, 5, and 6, and they're kind of like short answer, multiple choice kind of things. Try to do at least one of each one or two. They're not that much. You probably could do them all. You probably could figure it, because that could be, any of those questions could be asked. But I don't want you to feel like you're doing busy work. If you do a couple of them or all the way, then I think you'll get the hang of it. You just know the terminology, and it's kind of repetitive a little bit. Okay, here we go. So every year we usually have right before the AP exam. We usually have about 3 or 4 days to do electrochem at school. Not a lot of time, and so the good news is they do not require a lot of electrochem chapter on the AP. Probably only about 1/3 of what your textbook has is required for AP, and that's all we're going to mainly focus on. But even better than that, of that 1/3, some of it we went over earlier in the year in balancing redox equations. Do you remember how you balance an equation, and on one side you put you balance the atoms, and if I have oxygen, I got to add water on this side, and I got to add H plus on this side. Then I got to add electrons, make the charge. Well, if you don't remember how to do that, I'm going to I'll put the review videos up for that for you to go back and watch those. So that way it'll save time as well. Okay, so here we go. Now, the other thing is, when I made these notes many years ago, like probably 15 years ago even, I put all the information I could find in it. And then as years have gone by, thanks to people at UCLA like Mr. Walker, another person named Mr. Morgan, Mr. Urban at Venice, a lot of great, amazing mentor teachers that I love. Well, I realize there's a lot of stuff in here that we don't really have to focus or go over or focus on. A lot of it is kind of repetitive. So the best way I like to teach this now is just think about this. If you can do each day the homework problems, that you're good for AP. What they always do on FRQs is they give you what looks like a battery cell, and they want you to fill all the information in, ask questions, and make calculations about it. That's really all it is. So here we go. What is electrochemistry? The study, it says here, the study of interchange of chemical and electrical energy. What's really amazing, anytime you have an oxidation reduction reaction, okay, anytime you have a reaction like that, one substance loses electrons and another substance gains electrons. You remember that earlier in the year, Leo says Gur, lose electrons, oxidation, gain electrons, reduction. And I review it here in the beginning of this, but instead of going over all that, I'm going to let you just watch the video to review it. If you want to see that, I'm going to post that up here as well. I'll probably talk about the first one, but anyway, so this terminology, oxidized, reduced, well, in doing that, if the chemicals don't actually have to touch each other, they can actually react through a wire. If one substance can send electrons through a wire to another substance, then you've got electrical potential. You got electrical energy being produced. Really, really, really cool. And I'll talk about that. I'll talk about a scientist discovery that will pop up in a minute as we move along. So first, let's just take at least this one equation, and I want to say something about this, at least this first equation. Oh, and by the way, I know my notes say 17 or 18. What is it? I'll call it 17 for my class. Your textbook might be 18 now, but they moved it around as years have gone around. All right, look at this reaction. And let's just see. This is actually an oxidation reduction reaction. How can you tell if a reaction is a redox or oxidation reduction? Well, you have to label the charges of everything. Always start from the negative on. Sulfur, -2, magnesium, +2. Oxygen, any element in its free state is always 0. Okay? Like iron is always 0. Unless it has a charge, then it's +2 or +3. Okay? Now, so oxygen is 0. Magnesium oxide, that's -2, that's +2. SO2, that's -2, that's +4. Now, has anything changed in the reaction? The first easiest one I see, to me, real quick jumps out at me. Oxygen was 0, but now it changes to -2. Think about this. It goes from 0 down to -2. It was reduced. So oxygen is reduced to -2. Magnesium and sulfur. Sulfur -2, up, sulfur +4. Magnesium +2, +2. So sulfur is the one that changed. And I'll do it that way. It went from -2 to become +4. It went up. So one chemical will go down, reduced in charge. One goes up, and the one that goes up is oxidation. And remember, if you lose electrons, that's called oxidation. Gain electrons, reduction. We'll say more about that in a moment. So this will be an oxidation reduction reaction. Now, what you can also say is, since sulfide is reduced to S+4, I am so sorry, oxidized to +4. If they ever ask you on the AP, which substance is oxidized, justify, explain, you say, well, sulfur is oxidized because its charge, or oxidation state, should say, really, that's better to say it that way, but its oxidation state goes from -2 and increases to +4. Therefore, it is oxidized, undergoes oxidation. Or, which is reduced, oxygen is reduced because its charge, or you can say oxidation state, goes from 0 down to -2. It is reduced. The substance that is reduced by the other substance. So we say the oxidation, the one that undergoes oxidation is called the reducing agent. Another term for that. So you can say that sulfur reduces oxygen. It undergoes oxidation. It reduces oxygen. Okay. And the way we know that, oxidation, you lose electrons, right? The one that oxidizes, lose electrons. The one that is reduced, you add electrons to. It gains electrons. So one electrons is a product for, if you undergo oxidation, it gives off electrons. So this gives off electrons to oxygen. Oxygen gains the electrons. It is becoming reduced. Okay, because it's every electron makes your charge go down, 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 down. Okay, and so we call that also the oxidizing agent. These terms are not used that much anymore at all in AP, which is, well, oxidized and reduced are the important ones. This is the most important thing. But who oxidizing agent, who's reducing agent, they kind of stay away from that a little bit. But it's still good to know, as I told you, if something is oxidized, this one was oxidation, and it underwent oxidation, or oxidized. It was oxidized by, in this case, oxygen. That makes sense, okay? So it is the oxidizing agent. So this is, okay, the important thing are these. If you're reduced, you are the oxidizing agent. If you're oxidized, you are the reducing agent. Okay, enough of that. I'm not going to say any more. But kind of stay away from that a lot. That's why I had those little extra questions at the end to kind of help you on it. I mean, to kind of check you if you're, it's more of a vocabulary word stuff, you'll see. All right, so I'm going to go past the first pages of this, which are all reviewing the charges and all that. I'll find the notes for that, and I'll post a video. Then I go over balancing an acidic solution or balancing in basic. And you're not going to even have to really worry about that, because basic, they've never asked a question, a redox question where it was done in basic solution. Okay, so here's the fun part. Oh, my printer, I was using a low quality, but you can see the two scientists right there, Galvani and Volta. Two Italian scientists in 1700s. Doesn't that just sound like electricity when you hear those names? Volta, especially volt, voltage. Yes, volt was named after Volta. Well, here's what happens, and there's a little diagram I found from some other place. Look at that. Can you see what that is? It is, let's see if I can remember how to draw him. Oh no, do I remember how to draw him? I don't know if I remember how to draw him. How sad. I was trying to draw. Well, I guess I can do it this way. Yeah, it's supposed to be a little frog. And a little frog, his leg here, and a little leg there. The sad thing is, it's a frog who is being dissected. So, as you can see, just his legs are there. Poor little frog. But, hey, lots of science we got from that as well, right? But anyway, these scientists accidentally discovered something when they were probably, I guess, biologists, or they had lots of, maybe chemists, obviously chemists as well, but they had all these frog samples, and they noticed the frog was on a bronze hook. Now, bronze has in it brass, and the main thing we care about there is copper. It has copper and it also has zinc. No, I said brass. I'm sorry. Well, it's either bronze or brass. They both have copper. Bronze has tin, but brass has zinc, okay, with it. But we'll just say copper and tin. But man, think about the copper. So it has copper in the hook, and then that hook was hitting a post, hanging on an iron post. So you got copper metal, you got iron metal, and then you have a slimy. You know, he had some like salty. Imagine like salty solution all on him, on the body of the frog. What they noticed was the frog kicked. The legs were kicking. When they would hook it in the right way, they noticed a kick going on, even though that the frogs were not alive. And they called that animal electricity. What they were noticing is something pretty amazing. And I did this. Some of you may have seen the UCLA thing that we did, but I'm looking to see if I have any of the metals with me. Well, it's better than nothing. I have a couple of metal pieces I can show you real quick. Actually, I have, oh boy. Here's a piece of, this is this lead? Actually, oh no. This is aluminum. This is aluminum metal. This is magnesium metal, real thin. And this is copper. You've seen those. It was sticking in something in a solution. I had to clean that off. Well, anyway, the amazing thing that these two scientists realized was, if you touch any two metals together, remember, metals like to be positive. Metals like to lose electrons. We know that. They like to dissolve in water and stuff. Like sodium's a metal that wants to be Na+1. Potassium's a metal that wants to be K+1. Magnesium metal wants to be Mg+2. Well, if you touch any two metals together, one metal is going to give off electrons and the other one's going to gain electrons. But we don't see or notice anything. We don't have any shock. We can't notice anything happening just by touching them here, because really it's kind of like one gives an electron and the other one gives it back, and it's neutralized. Nothing happens. But they found that when you do that over a distance and you have them in a solution, that you can actually cause electrons to move through a wire or over a distance, electrical potential. That means you can make a battery. So what they realized was, any two metals you want to take, you can make a battery out of any two metals that you want. Now, how strong will that battery, how effective will it be able to power something? Well, that's something that was figured out later on by another scientist named Faraday, when he went through and mapped out, just a little bit later after them, what's called the standard reduction potentials. And this is going to be included in your notes. You'll see that as well. Okay, so if you have two metals, to me it is amazing, incredible to think that scientists got from that accidental little thing that we saw, and they got to what I'm going to show you right now, what's called a standard cell. So creating electricity by chemistry came first. And then after that came creating it by a generator in physics. That's really, in a way, that's not completely true. There was something that came before them called the Leyden jar. A German scientist, the last name I think Leyden, I believe that was right too. Or was his name? Yeah. That what he did, it should be. But what he did was, it's kind of like when you walk across a carpet and then you touch a doorknob and it shocks you. Okay, he found a way to store up static electricity in a little box, but then it would have like one little shock. He didn't really know what was going on or what he was doing. It's more like rubbing something, a comb against hair, or especially like if you have a cat and a really hard plastic comb, and you do that, even in the dark, you'll see sparks. So the Greeks knew about that. I've mentioned before, and they would take a resin, a hardened resin material from a tree, like a sap from a tree called amber, okay, and they would rub that against like the fur of an animal, and they would see these sparks that, and they called that electros. So electron came from that as well, the word. Okay, so what in the world? How are we going to make electricity with two metals? That's really what they realized, and we got to. I'm going to jump all the way through the notes, and I'll be telling you all these other words and notes along the way, like what is a coulomb, ampere, voltmeter, an instrument to measure the voltage of to tell you, is this battery how many volts? 1.5 volt, 9 volt, what is it? Okay, a galvanic cell, electrochemical cell. So I'm going to jump all the way over to standard reduction potentials in 17.2, and what I'm going to do, I am going to do a cell right under 17.2. I'm going to make a problem up. It's a lot like the one on your homework, but I'm going to change this. In the picture here, it has zinc and copper, but I want to use zinc and silver instead. So where you see copper, we're going to change that to Ag. And where you see Cu plus 2, we're going to make that Ag plus 1. But I'm going to explain the whole thing here. You may or may not, if you write small, you might be able to fit it here. But I'm just going to do this one problem for you right here. And okay. And I'm going to also jump ahead in history and talk about a man named Michael Faraday. Maybe, let me see if I copy the notes for him yet. His picture was in here. Oh, there he is, a few pages later for me. But there's Michael Faraday right there, England. And what he did, he pioneered electrochemistry, invented the system of oxidation numbers, discovered the law of electrolysis, and he popularized or created the terms anode, cathode, electrode, ion. From what I understand also, he did this. He mapped out all the elements. Think about what I said. Well, most all the elements that they knew at the time. Every metal, and said, okay, if I take, as I told you a moment ago, magnesium or iron, or copper or aluminum, or any of those, which one is going to be the absolute best metal that it will send electrons away? Think about that. When you send away electrons, you're LEO. You're losing. Who is the best LEO? Okay? Lose electrons in oxidation. Okay? Actually, I never thought about this till right now, but the best LEO on the chart is actually lithium, all the way at the bottom on this chart. Lithium is the best LEO. Isn't that good, easy way to remember? It's the best element that likes more to lose electrons than anybody. Who is the best element to gain electrons? Reduction. Well, on this chart, it is actually fluorine. But if I go down to find the metal, it looks like it will be, on this list, it will be cobalt metal. Cobalt plus 3 going to cobalt plus 2. But that might be a little bit hard to understand. So let's just go to gold. Look at gold. It's right, number 3. It will gain 3 electrons to become Au. Au plus 3 gains 3 electrons to become Au. Okay, so here's the deal about the standard reduction potentials. First, on the chart, as I said, what you should always look at when you see this chart is sometimes they're in reverse, okay? But fluorine we'll put at the top and lithium at the bottom. You've seen this earlier in the year. We talked about who is better at who's the best at being oxidized, who's the best at being reduced. So I'm going to put lithium at the bottom, fluorine here at the top, as it is on your list. And here's the deal. These are called reduction potentials. Who has the best potential to be reduced? The number one on the list, is fluorine. The lowest on the list, LEO, would be lithium. Okay? Now, here's the way it goes. A more positive number for what they call, this is called the cell potential or the voltage. Voltage is the spontaneous reaction. How about this, a better way to say it? A more positive E voltage stays as written. Okay? What do I mean by that? I'm going to show you. Fluorine, the reaction is gains 2 electrons to make 2F negative. Or could lithium gain 1 electron to become, could lithium plus 1 gain 1 electron to become lithium? Which of these is most likely to happen? This is a reduction, and that's a reduction. This is the number 1 reduction on the list, like the top 100. You know, they always count it backwards. Who's the number 1, the best reduced of all elements? It would be fluorine, because its number is positive 2.87. That's the voltage, the cell potential, they call it. Voltage or cell potential. Okay? Fluorine is positive 2.87. Lithium, though, look down here, is negative 3.05. Now, what's more positive? Well, obviously that is, because it's the only positive one. So what if I were to put together lithium and fluorine and make a battery out of that? I'll talk about how I can do it later. If I put lithium and fluorine, fluorine will keep this reaction. It will undergo a reduction because it is more positive. It will stay as written. That one. The more positive one stays as written. The more positive stays as written. The more positive stays as written in an electrochemical cell. The other one will be flipped around. Okay, so that will be gaining electrons, reduction. That has to become losing electrons, oxidation. So what's going to happen is you're going to flip it around. It becomes lithium plus, not plus, lithium turns into lithium ion plus an electron. And you flip around the charge to be positive 3.05 for that reaction. So that will occur in one cell and that will occur in the other cell. All right? If you remember those two, let's say we're not using fluorine. What if we're using, and I'll do it right now, I'm going to do a cell with zinc and I said silver. So we're going to look on the chart. We're going to go up about, I don't know how many that is, 10 or 11 or 12. And you see Zn plus 2 to gain 2 electrons gives you zinc. And the potential for that, for the zinc reaction, is negative 0.76 volts. Now, for silver, you have to go up, about 9 or 10 from the top, and you see Ag plus gaining an electron to give you Ag, and its potential is 0.80, and so it's a positive number. I didn't put the positive, but it is. So, if I make a battery and I use silver and I use zinc, which one of those is going, these reactions, these are the reductions, which reaction stays as written? The one that's more positive. Now, AP doesn't give this sheet anymore. They used to, but they don't. But what they do now is they give you these reactions. They just take about 4 or 5 of these off the list, and they might be mixed up, okay? So you got to really think about the positive number. So who's more positive? Oh, obviously silver. Positive will stay as written. But the zinc is more negative, and there it is. So it'll be flipped. It will be flipped around. And it becomes the oxidation half, and that's the reduction reaction. Okay, so what are we going to do with these, and how are we going to make a battery? That's the fun part, and here we go. So what I'm going to do, I'm going to use all this, but I'm going to write them down again in a moment. I'm going to draw it this way. First, you have, a lot of times we do it this way. It can be 2 separate containers, or it can be one cell with a little division down the middle. These 2 liquids cannot mix with each other, okay? There has to be a barrier. I think there's been a barrier there on the picture. I'm going to put a solution in each one. Now, why am I doing all these things? It's a long story, but think about how in thermo we have standard conditions. I guess that's the word. Temperature has to be this, 25. The pressure has to be 1 atmosphere. Molarities of anything has to be 1 molar. Okay? So I'm going to put a 1 molar solution of zinc nitrate. Now, it could be zinc nitrate or zinc, sulfate. I use sulfate here. I'm going to use 1 molar ZnSO4. I better write down below it. Now, the main thing that I care about for now are the zinc ions. Zn plus 2, Zn plus 2. And there'll be sulfate there too. I guess I better put a few sulfates. 2 and 2. Okay, on this side, I'm going to have 1 molar Ag. Oh, you know what? I can't use AgSO4 because it's a solid. I told you I want to use silver. You know what? I could use lithium instead. Why don't we make it lithium then? That'll be more fun. a lithium battery, LiSO4, Li2SO4. So you have lithium plus 1, and you have also, you'll also have sulfate. So it's easier in the picture just to change it to lithium. I told you it's silver, but oh well. Okay. Oh my goodness. You wouldn't want to use lithium at all in a battery. That would not work. You guys, this is bad news, because I had to put a piece of lithium metal in that, and it would react with the water. Well, there's no oxygen. I'll go on. No, what am I going to do? What am I going to do? I guess, yeah, lithium's going to react with the water. I better make it silver. I'll make it silver. But I'm going to have to use something else. I can't use sulfate there, because sulfate gives a solid. Remember the solubility rules? So we'll just make it silver nitrate over here. Oh well, we usually want to be consistent. But the nitrate's not going to be that big of a deal. We just need something negative. All right, so we got zinc over here, and we got also silver over here. In fact, I'm going to make a bigger container, because I got to tell you a little bit more about what's going to happen inside those containers. All right, in zinc, I'm going to put a bar of zinc metal. In the silver, I'm going to put a bar of silver metal. It doesn't matter how big that is, as long as there's some in and out of the solution. Then, what I'm going to do is I'm going to look over here. I'm going to connect them with a wire. And when I do that, in the middle, I'm going to put what's called a voltmeter. And that in the voltmeter is going to tell me it's going to measure and tell me how many volts do I get. I don't have to have a voltmeter. I can just put a wire and I'll see a spark go. But if I want to know what is that spark in voltage, I can find it out there. Now, my picture is not looking that great. I might have to fix this. Okay, here we go. Here's the bunch of stuff to tell you about these cells. In the half cell, I always recommend people do this. There's one more thing needed. It's called a salt bridge. A salt bridge, as it says here, bridges one side to the other. And what they normally do is they take like something like cotton, or maybe agar. Agar is what they call, they make in biology, the kind of a gelatin kind of material. And in that they put like a salt, like maybe sodium chloride. But we're not going to use sodium chloride. Let's use potassium chlorate. KClO3. So K is positive 1 and ClO3 is negative 1. I want to use a chemical that will not precipitate when it mixes with these. So zinc chlorate will not make a solid. Silver chlorate will not make a solid. Potassium nitrate will not make a solid. Potassium sulfate will not make a solid. So I want to use something like that. All right. Okay. So what's going to happen in my little cell? Doesn't look too great, but oh well. I'm going to see if I can. I guess you can kind of understand. Oh, I know what I can do. I can use other colors too. But let's make it a little bit bigger, because I will talk about the salt bridge in a moment. All right. One half is called the oxidation half cell. One is the reduction half cell. So let's figure out that from the reactions. Which reaction stays as written, we said? It's going to be the one with silver. In this chamber, here's what's going to occur. Silver ion, see them in the water? They're going to gain an electron to become silver. Okay, now, that will be the reduction. You know that's a reduction, so this is the GR half of the cell. The reduction half cell. Actually, reduction half cell. I'll write down here. Reduction half cell. They call it half because normally it's divided up into two parts. On this side, we have to flip it around, remember? And it's going to be zinc will undergo Leo, it'll be Leo, oxidation, to give you zinc plus 2 and 2 electrons. Okay? So that's the reaction that occurs in the left cell. Zinc gives you zinc plus 2 and 2 electrons. In this cell, you get silver gaining an electron to make Ag. This is the reduction half, because it's gaining electrons as reduction. It's going from positive 1 down to 0. This is the Leo half. It loses electrons, undergoes oxidation from 0 up to positive 2. So that's the oxidation half cell. Or I'll just say half cell or oxidation cell. Okay, now another thing interesting occurs. But before I do that, I'll go on and I'm going to, well, actually, let me show you one more thing. They like to say a lot of times, what is going to happen? What's going to be what's going to be the direction of electron charge flow? Is it going to flow from the silver over to the zinc, and they'll come through the bridge? Will negative charge go this way? That we'll call that clockwise, or will it go counterclockwise? Am I get it right? Or will it go clockwise from zinc to silver and then back through and all that? Okay. Well, the way to figure that out is look at this. Electrons are produced by this reaction. So electrons are given off. Here, electrons are taken in. So electrons will come to this side. They'll leave this side. Their product. They're going to go that way in my drawing, and they're going to go. It'll be clockwise. They're going to go here, and then charge will go through. I'll say more about that charge in a later lesson about what's actually going on there. But let me show you how to calculate the cell potential. Again, this is just the first lesson, and I'll try and say more details next time. So in the what I'll do is I'm going to put together those two reactions I showed you right here. Silver plus an electron gives you Ag, and the cell potential for that we said was silver 0.80. The zinc one we had to flip around backwards. I'm sorry. Yeah, well, it doesn't matter. I'd like the arrows to be lined up. And it is going to be negative zinc 0.76. Negative 0.76 volts. Now, okay, hold on. It was negative 0.76. Remember that I got to flip it, and it will become positive 0.76. Okay, negative as it was written in a reduction. What was zinc plus 2 electrons gives you zinc. That was negative, but this is now going to be positive when you flip it around. Well, the other thing you're going to have to do is multiply to make the electrons cancel out. I have to multiply all this by 2. So 2 silver, 2 electrons, 2 silver, and it will be 2 times that voltage. So it's going to be 1.60 volt now. So that becomes 1.60. Now, when I combine the two equations, look at what happens. First, I'll get the balanced equation. 2 silver ion plus zinc. Because these 2 electrons and these 2 on the right and the left, they both cancel. So 2 silver ions plus zinc gives you 2 silver ions plus zinc ion. And the voltage, just add them up. So 1.60 and 0.76 gives you 2.36 volt. What does that mean? It means this little battery is 2.36 volts. 2.36. Now, you know what a 9-volt battery is? The little round batteries you put in remote controls, the little cylinder batteries, those are pretty much all 1.5 volts. So this is stronger than that little battery, but less than a 9-volt battery. Okay, another thing you need to know. The reduction half cell, there's another little terminology besides Leo says Gur, and that is the anode. They call these two things electrodes. This is an electrode and that's an electrode. But the electrodes have names too. The anode is where oxidation occurs. Okay? The cathode is where reduction occurs. So an easy thing to do, somebody once thought, well, maybe they were an English teacher taking chemistry, and they said, look at this. A-O, those are vowels. A-O, vowel. And look at C and R for reduction. Those are consonants. So vowels, A are going to be anode is where oxidation, and the cathode is where reduction occurs. So because of that, we call this oxidation cell the anode. We call this reduction cell, this is called the cathode. The anode consists of zinc in zinc plus 2 solution. The cathode consists of silver metal, and silver solution, Ag plus 1 solution. Okay, is there anything else to tell you here? You know the cathode, you know the anode. Okay, some of the terminology. I think this is enough to do the first problem that you'll do. It'll ask you questions to analyze. Like, for example, as I said, Well, we know we already said this one's going to go clockwise. Then in this reaction, zinc undergoes oxidation. Okay, it loses 2 electrons. It goes from charge of 0 to positive 2. Silver undergoes reduction. It changes its charge from positive 1 to 0. Also, as the cell goes by, as it progresses, you should know that zinc releases 2 moles of electrons, and silver will gain 2 moles of electrons. So that's how they react. 2 moles of electrons cause this to occur. Oh, I know what I forgot to tell you. The mass. Okay, here's a weird thing. The reaction tells you everything that is occurring. Zinc is a solid right here. This is the zinc metal, and it is dissolving. So as time goes by, zinc plus 2 dissolves off from the anode, from the electrode, from the zinc bar. Its mass, it gets smaller and smaller. This one gets smaller as time goes by. Notice the ions dissolve off, but what does it leave behind? The negative electrons. And the electrons get sent the other way. Okay? So it builds up negative, and that's why, boom, boom, gets rid of them there. Well, on this side, the opposite happens. The silver ions that are here, Ag plus 1 in the solution, they are going to plate, and they're going to join on the cathode. The cathode is going to get larger, the Ag bar, and you can tell from the equation, it was Ag plus 1 dissolved, and it becomes solid silver. That's a solid, remember. That's also a solid for the zinc there. So here the solid dissolves. Here it precipitates, where it increases in mass. Another thing also happens, the molarity. What's going to happen to the molarity? So the mass of this side will increase. The mass of the electrode, we'll say, which is the cathode. Here the mass of the electrode decreases. All right. Wow, I'm sorry, my chalk just broke. You saw it. I'm rushing now because I got to do something else. Okay, the mass electrode decreases here. Another thing that happens is this, kind of neat. The molarity. This starts out 1 molar AgNO3, but remember, the silver ions are going to be going and joining onto this, so the molarity decreases. The molarity of Ag plus 1 decreases as time goes by, as you run the cell. Here, the molarity of Zn plus 2 is going to what? Remember, the zinc metal dissolves and it adds more and more zinc plus 2 ions here. It increases. And I'll say more about this next thing later, but I'll just throw it in real quick. Every time an ion comes off from here to there, this becomes very positive, this chamber. And so what happens in your salt bridge, because it's positive, something negative is going to come out. Chlorate ions are going to come out, and they're going to migrate out into this cell to balance off. So you're going to get 2 chlorates come in here to balance off the zinc. On the other side, every time you lose a silver, you're going to lose a positive. So a potassium is going to come out of the salt bridge. And if the salt bridge runs out of potassium and chlorates, then the battery will be stopped, will be over. All right. This is plenty enough to do the first lesson. Oh, and the only thing I didn't really make a big deal about was this. If you're comparing on this chart, like who can oxidize who can reduce who, that kind of thing. Well, lithium is the best, we said Leo, oxidizer, and then that will be, fluorine will be the best I'm sorry. No. I said that bad. Leo is the best to be oxidized. That means it's the best reducer. That is the best reduced. That's the best to undergo reduction. That's the best to undergo oxidation. Ger and Leo. So if I'm comparing fluorine and chlorine, we say, well, all right, who is the better to be reduced? Fluorine. Who's the better oxidizer? Oxidized is chlorine. Chlorine is the best to be oxidized. Fluorine is the best to be reduced. Fluorine would be the best oxidizing agent. So it would be the best at oxidizing chlorine. But fluorine could not reduce chlorine. It would be impossible because fluorine undergoes reduction itself. So it can be reduced, but it can oxidize chlorine. It can't reduce chlorine. Chlorine is the best Leo. It's the best to be oxidized. So that means it can reduce fluorine, but it cannot oxidize fluorine. So a lot of this is just terminology stuff, and I'll say more about it when we see the Zoom on class. But that's what I just said. Just try to answer those little questions. But it's kind of a minor thing for AP now. They want you just to know who is LEO, who is GER, what does that mean in terms of equations, who's giving up electrons and who's gaining it. That's really all I think that's really all they care about. But the book you have talks about who's the oxidizing agent, who's reducing, who can oxidize this, who can reduce this, that kind of thing. All right, I'll see you guys. Thank you.